Pressure and fluid statics. This topic discusses pressure and static fluids as a foundation of fluid mechanics. Pressure is understood as force per unit area, acting within a fluid. A fluid at rest exhibits special behavior because no shear stress exists. These concepts are essential to analyze dams, tanks, and hydraulic systems. The discussion focuses on force balance and pressure distribution. Lesson Plan: Fluid Mechanics 1. The course structure consists of 8 main chapters that gradually build understanding of fluid mechanics. This chapter comes after basic concepts and fluid properties. Pressure and fluid statics serve as a bridge toward flow analysis. Each chapter is interconnected and forms a complete physical model of fluids. The sequence is designed to move from static to dynamic concepts. Learning outcome. The learning outcomes emphasize the ability to analyze pressure, manometers, and hydrostatic forces. Students are expected to calculate forces on plane and curved surfaces. Stability of floating and submerged bodies is also a key focus. In addition, fluid behavior under acceleration and rotation is analyzed. These outcomes prepare the foundation for real engineering applications. Stress distribution insights. Pressure depends on weight and the area over which the force acts. With the same foot area, a heavier person produces higher pressure. This shows that pressure is determined not only by force, but also by area. This concept is important in footwear and structural support design. Mathematically, pressure is defined as P equals F divided by A. Pressure gauges overview. Pressure gauges are available in many sizes and scales for different applications. Accurate pressure measurement is crucial for safety and system efficiency. These devices are designed to withstand harsh industrial environments. Without pressure measurement, fluid systems cannot be properly controlled. Therefore, pressure measurement is a key part of engineering practice. Check your understanding number 1. Different sizes and scales of pressure gauges cater to diverse applications, providing accurate readings critical for safety and system efficiency. Pressure types overview. Different types of pressure are used depending on the measurement reference. Absolute pressure is always positive because it is measured from vacuum. Atmospheric pressure is often used as a practical reference. Gauge pressure is commonly used in engineering applications. The relationships among these pressures must be understood in fluid system analysis. Pressure as a scalar. Pressure at a point in a fluid acts equally in all directions. This shows that pressure is not a vector quantity, but a scalar. This property greatly simplifies force analysis in fluids. The direction of the pressure force depends on the surface orientation, not on the pressure itself. This concept is fundamental in hydrostatics. Fluid element equilibrium. A small fluid element must be in force equilibrium in order to remain at rest. The acting forces include pressure forces on each face and the weight due to gravity. The distribution of pressure forces depends on the orientation of the element surfaces. This equilibrium is the basis for deriving the hydrostatic pressure equation. From this concept, it can be shown that pressure acts equally in all directions. Correct answer: B. Gravity affects the vertical pressure distribution in the fluid, contributing to equilibrium. Explanation of incorrect options. Option A, gravity influences vertical, not horizontal pressure variations. Horizontal pressure differences are generally due to flow or external forces. Option C, gravity does not eliminate the need for pressure forces. Both forces work together to maintain equilibrium in the wedge. Option D, gravity does not ensure uniform pressure distribution. Instead, it causes a pressure gradient, with pressure increasing with depth.
Fluid pressure variation. Pressure in a static fluid increases as depth increases. This increase is caused by the weight of the fluid above the point. The pressure distribution follows a linear relation with depth if density is constant. As a result, walls and bottoms of containers experience larger forces at greater depths. This concept is essential in the design of dams and tanks.
Fluid element forces. A fluid element is subjected to pressure forces on all sides, and its weight acting downward. For a static condition, the sum of all forces must be zero. This equilibrium applies in both horizontal and vertical directions. From this, the relation between pressure change and depth can be derived. This principle is the foundation of the hydrostatic equation. Pressure in gases. In a space with limited height, such as a room, the variation of air pressure is very small. The pressure difference between the floor and the ceiling is usually negligible. Therefore, gas pressure is often treated as uniform in many engineering applications. This assumption simplifies the analysis of systems involving gases. Unlike liquids, gas pressure changes with height are much smaller.
Liquid pressure variation. In a static liquid, pressure increases linearly with depth from the free surface. At the surface, the pressure equals atmospheric pressure. The deeper a point is located, the higher the pressure, due to the weight of the liquid above it. This relation can be written as P equals P atmos plus rho g h. This equation is one of the most important in hydrostatics.
Check your understanding. Number 3. In a static liquid, pressure rises linearly with depth, starting from atmospheric pressure at the free surface.
Hydrostatic pressure overview. Hydrostatic pressure depends only on depth, fluid density, and gravity. At the same horizontal level in the same fluid, the pressure is always the same. Atmospheric pressure only adds to the pressure at the surface. The shape and geometry of the container do not affect horizontal pressure distribution. Denser fluids produce higher pressure at the same depth.
Hydraulic jack principle. This principle is based on Pascal's law, which states that pressure is transmitted equally in all directions. A small force acting on a small piston can produce a large force on a bigger piston. This relation follows F1 over A1 equals F2 over A2. With this principle, heavy loads, such as cars, can be lifted using relatively small forces. Hydraulic systems are widely used in industrial and automotive equipment.
Basic barometer. A barometer measures atmospheric pressure using the height of a mercury column in a closed tube. The top of the tube is nearly a vacuum, so the mercury column is supported by atmospheric pressure. The height of the column is directly proportional to atmospheric pressure. The higher the atmospheric pressure, the taller the mercury column that can be supported. This principle forms the basis of classical atmospheric pressure measurement. Barometer fluid column. The height of the fluid column in a barometer is not affected by the length or cross-sectional area of the tube. The determining factors are only atmospheric pressure and fluid density. The tube diameter must be large enough so that capillary effects can be neglected. This shows that the barometer works based on pressure balance, not fluid volume. This concept reinforces the fundamental nature of hydrostatic pressure.
Check your understanding. Number 4. Correct answer, C. The atmospheric pressure and fluid density, independent of tube dimensions. Explanation of incorrect options. Option A.
The height of the fluid column does not depend on the tube's length or diameter, provided the tube is large enough to avoid capillary effects. Option B. The material of the tube does not affect the fluid column height, as long as the tube allows fluid to flow and does not significantly react with the fluid. Option D. The surface area of the exposed fluid does not determine the height. Only atmospheric pressure and fluid density govern the height of the column.
Altitude effects. At higher altitudes, air density becomes lower, so pressure and oxygen content decrease. This causes combustion engine performance to drop due to reduced oxygen supply. Humans also experience this effect as shortness of breath and reduced stamina. This phenomenon shows the relationship between pressure, density, and system performance. This concept is important in aerospace and automotive engineering. Pressure variation in solar pond. In a solar pond, fluid density can vary with depth, so the pressure distribution is no longer perfectly linear. In the gradient zone, pressure still increases with depth, but at a different rate. Density variation affects how thermal energy is stored in the pond. Analysis of pressure and density is essential to understand system performance. This example shows the limitation of the constant density assumption. U-tube manometer. A U-tube manometer is used to measure the pressure difference between 2 points. Its working principle is based on pressure equilibrium in a static fluid. The difference in fluid column heights indicates the pressure difference. The larger the pressure difference, the larger the height difference. This device is simple but very accurate for basic measurements. Basic manometer. A basic manometer compares gas pressure with atmospheric pressure using a liquid column. The height difference of the liquid column is proportional to the pressure difference being measured. This device is suitable for measuring low to moderate pressures. Its analysis directly uses hydrostatic equilibrium. This concept is widely used in laboratories and simple systems. Check your understanding number 5. Gas pressure measurement using a U-tube manometer relies on the height difference in the liquid column, which is proportional to the pressure being measured. Stacked fluid layers. If several fluids with different densities are stacked, pressure increases through each layer. The contribution of each layer to the total pressure depends on its density and thickness. The pressure at the bottom is the sum of the pressures from all layers. Denser fluids contribute more to the total pressure. This principle is important in layered fluid system analysis. Differential manometer. A differential manometer is used to measure the pressure drop between 2 points in a flow system. The difference in fluid column heights reflects the pressure difference. This device is very useful for analyzing pressure losses in pipes and equipment. Its working principle is still based on hydrostatic equilibrium. With this tool, flow system performance can be quantitatively evaluated. Bourdon tubes overview. A Bourdon tube converts fluid pressure into mechanical displacement that can be read by a pointer. When pressure enters the tube, the flattened tube tends to straighten. This shape change is then translated into pointer movement on a scale. There are various designs, such as C-type, spiral, and helical for different pressure ranges. This principle is widely used in industrial pressure gauges. Dead weight tester. A dead weight tester is used to measure and calibrate very high pressures with high accuracy. The device works using a piston and calibrated weights to generate a known pressure. The pressure is calculated from the applied weight divided by the piston area. A fluid, such as oil, is used to transmit the pressure steadily. This instrument serves as a reference standard in pressure gauge calibration. Hydropower. Hydropower plants use water pressure and flow
to generate electricity. Water is stored at a certain height, so it has large potential energy. When it flows through turbines, this energy is converted into mechanical and then electrical energy. Dam structures must be designed to withstand very large water pressures. This system shows a direct application of hydrostatic pressure concepts.
Hydrostatic force analysis. In many cases, atmospheric pressure can be neglected because it acts equally on both sides of a surface. What remains is only the hydrostatic pressure due to the fluid column. This approach simplifies the calculation of forces on submerged surfaces. The hydrostatic force depends only on depth, density, and area. This concept is very important in submerged structure analysis. Check your understanding number 6. Correct answer? C, because atmospheric pressure cancels out if it acts equally on both sides of the fluid interface. Explanation of incorrect options. Option A. Atmospheric pressure does affect submerged objects, but it is not included in calculations when it cancels out on both sides. Option B. Atmospheric pressure is not negligible. It is significant, but can be omitted in specific cases due to equal application on both sides. Option D. Hydrostatic pressure applies to liquids and gases, so this statement is incorrect. Hydrostatic pressure is a function of depth and density. Inclined surface hydrostatics. On an inclined surface, pressure still increases linearly with depth. As a result, the force distribution is not uniform and produces a moment about a reference point. The resultant force acts below the geometric centroid of the surface. The pressure prism concept can be used to visualize the total force magnitude. This analysis is important for gates and other inclined structures. Pressure on inclined surface. The pressure at the centroid of the surface equals the average pressure over the entire area. This average pressure is determined by the depth of the centroid from the free surface. The total force is then obtained by multiplying the average pressure by the surface area. This approach greatly simplifies hydrostatic force calculations. However, the location of the line of action must still be determined separately. Resultant force on surface. The magnitude of the resultant hydrostatic force equals the average pressure multiplied by the surface area. The line of action of this force does not pass through the geometric centroid, but through the center of pressure. The center of pressure is always located deeper than the centroid. This is due to the pressure distribution increasing with depth. This concept is very important in the design of fluid-retaining structures. Check your understanding number 7. The resultant hydrostatic force on a submerged surface equals the average pressure multiplied by the surface area, and its line of action passes through the center of pressure below the centroid. Centroid and moment of inertia. Each area shape has a different centroid location and moment of inertia. The centroid location determines the effective depth for average pressure calculation. The moment of inertia is used to determine the position of the center of pressure on a submerged surface. Shapes such as rectangles, circles, and triangles have different formulas. This concept is essential in hydrostatic force analysis for various geometries. Pressure prism concept. The hydrostatic force on a surface can be visualized as a pressure prism. The length of the prism represents the pressure magnitude, while its base is the surface area. The volume of this prism is proportional to the total force acting on the surface. This approach helps explain why force increases with depth. This concept simplifies the visualization of pressure distribution. Hydrostatic force on plates. The hydrostatic force on a plate depends on its orientation relative to the free surface. On a vertical plate, pressure increases linearly from top to bottom.
On a horizontal plate, pressure is uniform because all points are at the same depth. On an inclined plate, the pressure distribution is still linear, but the force direction changes. These differences affect the force magnitude and the center of pressure location.
Check your understanding number 8. Correct answer, B. The force depends on the tilt angle and pressure distribution, with the center of pressure shifting due to varying pressure gradients. Explanation of incorrect options. Option A, the hydrostatic force does not remain constant. It varies with the tilt angle and pressure distribution, and the center of pressure also shifts due to gradients. Option C, the center of pressure does not always remain at the centroid. It shifts below the centroid due to the non-uniform pressure gradient. Option D, the hydrostatic force is directly related to depth, not independent of it. Plate width affects surface area, but not the fundamental depth-pressure relationship. Curved surface structures. Curved surfaces are used to distribute pressure more efficiently than flat surfaces. The curved shape increases structural strength and reduces stress concentration. Therefore, large dams are often designed with curved surfaces. Very large water pressures can be transmitted more safely to the structure. This concept shows the importance of geometry in engineering design. Hydrostatic force on curved surfaces. The hydrostatic force on a curved surface is analyzed by separating it into horizontal and vertical components. The horizontal component equals the force on the vertical projection of the surface. The vertical component equals the weight of the fluid above the curved surface. The resultant force is obtained by combining these two components. This approach simplifies the analysis of complex shapes. Curved surface forces. On curved surfaces, the vertical hydrostatic force acts opposite to the weight of the fluid above it. The horizontal force component must still be considered for structural equilibrium. Both components determine the direction and magnitude of the resultant force. Proper analysis is essential for the design of large structures, such as dams. Errors in force estimation can lead to structural failure. Circular surface forces. On a circular surface, the hydrostatic force acts through the center of the circle. This occurs because the pressure distribution is symmetric about the center. All pressure forces act normal to the surface and converge at one point. Geometric symmetry greatly simplifies the force analysis for this shape. This example shows the important role of symmetry in fluid mechanics. Check your understanding. Number 9. In a circular surface submerged in a fluid, the hydrostatic force acts through the center of the surface, with pressure forces perpendicular to the surface due to the symmetry effect of the geometry. Multi-layered fluid forces. If a surface is in contact with multiple fluid layers, the force must be calculated separately for each layer. Each layer contributes a force according to its density and depth. The total force is obtained by summing all these contributions. Denser fluids have a larger influence. This approach is important in stratified fluid systems. Flat plate submerged. The force on a thin submerged plate does not depend on the plate thickness, but on the fluid density, depth, and plate area. In symmetric conditions, pressure forces on both sides may cancel each other out. If only one side is submerged, a net force will act on the plate. The buoyant force concept is also related to the volume of displaced fluid. This analysis is important in thin structure design. Buoyancy and submerged bodies. The buoyant force acts upward through the centroid of the displaced fluid volume. The magnitude of this force equals the weight of the displaced fluid. The weight of the body itself acts through its center of mass. If the body's weight is greater than the buoyant force, the body will sink. This principle is known as Archimedes' principle. Check your understanding number 10. Correct answer, C. When the solid's weight exceeds the buoyant force acting upward, indicating greater density. Explanation of incorrect options. Option A. This is incorrect because a solid body will float if the fluid's density is greater than the solid's density, not sink. Option B. If the solid's weight is less than the buoyant force, the body will float, not sink. Option D. When the buoyant force and the solid's weight are perfectly balanced, the body is in equilibrium and does not sink, but remains suspended or floats.
Density and buoyancy. The behavior of a body in a fluid is determined by the comparison between the body density and the fluid density. If the body density is smaller, the body will float. If the densities are equal, the body will remain neutrally buoyant. If the body density is larger, it will sink. This concept is very important in the design of ships and floating structures.
Hot air balloon dynamics. A hot air balloon works by reducing the air density inside the balloon through heating. When the inside air density becomes lower than the outside air, the buoyant force becomes greater than the balloon's weight. The balloon altitude stabilizes when the buoyant force equals the total system weight. Additional heating makes the balloon rise, while cooling makes it descend. This system is a direct application of the buoyancy principle. Stability analysis. Stability of a system can be classified as stable, neutral, or unstable. In stable equilibrium, the system returns to its original position after a small disturbance. In neutral equilibrium, the system stays in its new position after being disturbed. In unstable equilibrium, the system moves further away from its original position. This concept is widely used in mechanics and structural analysis. Buoyancy and stability. For floating bodies, stability is determined by the positions of the center of gravity and the center of buoyancy. If the center of gravity is below the center of buoyancy, the system tends to be stable. If they are aligned, the system is neutrally stable. If the center of gravity is above the center of buoyancy, the system becomes unstable. This analysis is very important in ship and marine structure design. Check your understanding number 11. In stable equilibrium, the center of gravity is located below the center of buoyancy, allowing the body to return to its original position after being tilted. Restoring stability. If the center of buoyancy and the center of gravity are not vertically aligned, a restoring moment will appear. This moment acts to return the body to its equilibrium position. This explains why a stable body returns upright after being slightly tilted. This mechanism is very important in the stability of ships and floating structures. Without a restoring moment, the system would easily overturn. Stability of floating bodies. The stability of floating bodies is strongly influenced by the position of the metacenter relative to the center of gravity. If the metacenter is above the center of gravity, the body will return to its original position after being tilted. If the metacenter is below the center of gravity, the body becomes unstable and tends to overturn. Ships are often designed to be bottom-heavy to lower the center of gravity. This concept is central to ship stability analysis. Trough stability. A system like a ball in a trough shows stability for small disturbances. If the disturbance is large enough to move the ball out of the trough, stability is lost. This shows that stability depends on geometric limits. This example is often used to explain the difference between local and global stability. This analogy helps visualize the concept of stability. Vertical force balance. For a static fluid element, the pressure forces from the top and bottom must balance the weight of the element. This balance ensures that there is no vertical acceleration of the fluid.
The pressure difference between two elevations is what supports the fluid weight. From this, the basic relation between pressure change and depth is obtained. This concept is the foundation of the hydrostatic equation.
Check your understanding. Number 12. What ensures vertical equilibrium in a static fluid? Correct answer, B. The balance between pressure differences on top and bottom surfaces and the fluid element's weight. Explanation of incorrect options. Option A, horizontal pressure forces do not contribute to vertical equilibrium. They are relevant for horizontal force balance, but not for vertical stability. Option C, pressure gradients exist in static fluids due to depth. Their presence is necessary for balancing the fluid's weight. Option D, body force, weight, acts downward, but equilibrium depends on the interplay between body force and vertical pressure differences, not uniform distribution.
Hydrostatics in motion. If a container moves with constant velocity, the fluid inside still behaves like a static fluid. There are no additional forces due to acceleration that affect the pressure distribution. Therefore, the hydrostatic equations are still valid in this condition. An example is water in a glass carried at constant speed. Pressure changes only when acceleration is present. Acceleration effects on pressure. When a system experiences acceleration, the pressure distribution is no longer purely hydrostatic. In free fall, the pressure becomes uniform throughout the fluid. If the system accelerates upward, the pressure at the bottom increases. This shows that acceleration effectively adds to or subtracts from the effect of gravity. This concept is important in the analysis of moving tanks and rockets.
Motion effects on liquid in tank. Horizontal acceleration causes the free surface of a liquid to tilt. This tilt occurs because the effective gravity direction is a combination of gravity and acceleration. Pressure still increases linearly along the direction of this effective gravity. The free surface is always perpendicular to the effective gravity direction. This phenomenon is often seen in accelerating vehicle tanks.
Constant pressure in accelerating liquid. In a fluid undergoing acceleration, constant pressure lines are no longer horizontal. The direction of these pressure lines follows the projection of the effective acceleration vector. Pressure still increases linearly with depth measured along that direction. The free surface of the fluid is always perpendicular to the effective acceleration direction. This concept extends hydrostatic principles to accelerated systems.
Check your understanding. Number 13. On an inclined free surface, the pressure increases linearly with depth, while the pressure lines align with the projections of the acceleration vector.
Rotating liquid in a cylinder. If a liquid is rotated inside a cylinder, its free surface forms a parabolic shape. This shape occurs because of the balance between centrifugal force and gravity. Pressure increases radially outward and also with depth. The pressure distribution is no longer only a function of vertical depth. This phenomenon is important in many rotating engineering applications. Pressure surfaces in rotating liquid. In a rotating fluid, constant pressure surfaces form paraboloids. All these pressure surfaces have the same shape as the free surface. Pressure increases both radially and vertically. The free surface is the topmost constant pressure surface. This concept helps visualize the three-dimensional pressure distribution. Spinning liquid mercury mirror. This telescope mirror uses rotating liquid mercury to form a very precise parabolic surface. This parabolic shape is ideal for focusing starlight. By exploiting the natural behavior of rotating fluids, manufacturing costs can be reduced. This system shows a direct application of fluid mechanics in astronomy.
simple physical principles can produce very advanced technology.
Check your understanding number 14. What is the primary advantage of using a liquid mercury mirror in a large zenith telescope? Correct answer, B. The spinning motion naturally creates a parabolic surface, ideal for focusing light. Explanation of incorrect options. Option A. While the liquid mirror benefits from its self-forming parabolic shape, precise alignment and calibration are still needed for other parts of the telescope to ensure accurate observations. Option C. Liquid mercury mirrors are limited to observing objects near the zenith and cannot scan all areas of the sky due to their fixed orientation. Option D. The mirror's liquid surface can be affected by vibrations or environmental disturbances, requiring careful control to maintain its shape.
References. This chapter refers to the book by Eunice A. Chengel and John M. Chimbala as the main source. All pressure and fluid statics concepts follow the approach and notation of this book. This reference is one of the most popular resources in engineering fluid mechanics. A good understanding of this book greatly helps mastery of the subject. Many examples and illustrations are taken from this source.